Hello and welcome to Unit 2, Lesson 6, Compounding the Problem. In this lesson, we're going to learn about a very famous number, the number E. And if you've never heard of that before, well, enjoy the experience. So here we are in part 1. It says, as an enterprising young mathematician, you know that superior knowledge of mathematics will help you make better decisions about all kinds of things in your life. One important area is money. So you've been contemplating the world and wondering how you could maximize the money that you make in your savings account. You're young and you haven't saved much money yet. As a matter of fact, you only have $100, but really want to make the best of it. You like the idea of compound interest, meaning that the bank pays you interest on all the money in your savings account, including whatever interest that they had previously paid you. This sounds like a very good deal. You even remember that the formula for compound interest is exponential. And here it is. This was actually introduced in Integrated 1 in Unit 2, I believe. And it lists what all of the parameters are here. So A is the amount of money at any time. P is the principal. That means the original amount you put into the account. R is the annual interest rate. That must be as a decimal. And N is the number of compounding periods each year. That means how many times do you compound? And T is the number of years. So number 1, if your savings account pays a generous 5% per year, and that is pretty good, and is compounded only once each year, how much money would be in the account at the end of 1 year? So the amount is equal to 100 times 1 plus the interest rate, 0.05. So we had to change this to its decimal form, divided by 1 compounding to the power of 1 compounding times 1 year. So essentially that's just 100 times 1.05. Should be 105. All right, let's put a dollar sign on it. And no cents. So that would be very simple interest, probably the least amount of money you could make. But number 2, how much money would be in the account at the end of 20 years? Okay, that would be 100, 1 plus 0.05. And then we're still compounding once a year, but we're doing it 20 years. So that's 100, 1.05 to the 20th. And that is, and we're going to round this on paper, but in our calculator, we would just leave it with all of its decimals. 265.33. So $265.33. Wow, the money has more than doubled after 20 years with just a very modest 5% interest rate. Next page. It seems like the more compounding periods in the year, the more money you should make. The question is, does it make a big difference? So they want us to do a little experiment where we compare the amount of money after 20 years if it's compounded 2 times a year, that's called semi-annually, 4 times a year, that's called quarterly, 12 times a year, that's monthly, 365 times a year, that's daily, and then hourly, well, you could just take 365 and multiply it by 24. Find a way to organize, display, and explain your results to your class. So I thought that the best way to do that would be to use Desmos. And so here comes Desmos right now. And as you can see, I've typed in the formula but I've left the number of compounding periods as x. There's my 2 times a year, 4 times a year, 12 times a year, 365. Then I just did 365 times 24. I mean, I don't really need to know what that number is. And then I went up as high as 1,000,000. It turns out the value you found in your compounding problem is 100 times a very famous irrational number named e. Because e is irrational, that means it can't be written as a fraction. It's non-terminal, it's non-repeating. It's a number like pi. And here's some of the digits of e. I would say memorize 2.718. That ought to be enough. Kind of like memorizing pi, 3.14. Then it says, like pi, e is a number that occurs in the mathematics of many real-world situations, including exponential growth. One of the formulas using e results from the thinking that you just did about compound interest. It can be shown that the amount of money, A, in a savings account where the money is compounded continuously. So that's every fraction of every second and every fraction of a fraction you could think of. Just it's split into so many tiny little bits. You would think that would just go to infinity, but no, it stabilizes around a number, e. So here's our formula for continuous growth. This would be how natural things grow. Like, for example, if you put bacteria into a petri dish, it would grow this way. At least for a little while, till it ran out of food. So again, P is the principal, R is the interest rate, T is the time in years. It is fairly typical for savings accounts to be compounded monthly. Compare the amount of money in 2 savings accounts after 10 years with the same initial investment of $500 and an interest rate of 3% in each account. If the first account is compounded monthly and the second account is compounded continuously. So here's the first account. The amount is 500 and then 1 plus 3% split into 12 equal parts to the power of 12 times 10. So 12 times 10 means in 10 years, they're going to calculate your interest 120 times. Okay, that number, just give me a second to look that up. That number is 674.68. Now, the other way to do it continuously is 500 e to the interest rate times the time. And the time was 10 years. That value is 674.93. So there isn't a very big difference between the two, but there is a difference, and continuously is always going to win. It says, use technology to compare the graphs of the 2 accounts. What conclusions would you draw about the effect of changing the number of compounding periods on a savings account? So we put the 2 graphs up, and what you're going to find is that you really can't tell the difference between the graphs. The separation becomes wider as the years go on, but basically at the beginning you can't really tell much of a difference. So, part 2. Since E is widely used to model exponential growth and decay, let's get a little bit more familiar with this exponential. Make a prediction about the graph. Explain what prior knowledge you used to make your prediction. So you think about it, it should look like any other exponential, such as 2 to the x or 3 to the x. It says create a table and a graph and describe the mathematical features of f of x. This is a great thing to do on Desmos. And so when they talk about features, they're talking about domain. So domain is going to be negative infinity to infinity. The range is going to be from 0 to infinity. And it's going to contain the point. So this, remember, we called this our tracking point or our reference point. Contains 0, 1. And it's always increasing. And let's learn how to spell increasing. C-R-E-A-S-I-N-G. The whole interval of the domain. It's increasing. Okay, and then let's look to our takeaways. The features here would be pretty much the same thing we just wrote down. There is a horizontal asymptote. Let's write that one down. Asymptote at y equals 0. And everything we wrote before. Okay, so E is about 2.718. E is an irrational number. It means you can't write it as a fraction. Irrational number used to model growth and decay. To model growth and decay in sort of natural situations. See, nobody tells a bacteria, "Oh, it's time for you to divide." It's just sort of a natural process. It's not artificial. So E is a better description of that process. All right, that's it. We'll see you next time.